Before we start modeling a specific type of internal combustion engine, I want to summarize sort of a key distinction or categories of air standard cycles. And the reason is that students, including myself, have had a tough time understanding the difference between two key categories of thermodynamic process modeling. And so in homework problem assignments for this textbook, the author will specify in a homework assignment two types of ways to analyze or ways to model the air. And you're going to see two key words, cold air standard, and then just the words air standard. And I want to give you some notes on how to approach those two different types of models because it was so confusing to me. And I'm hoping that some of this material will help clarify it for you before you get started. And so we're still in section 9.1. And also you'll see, wow. And so this particular slide goes all the way back to 2024, in which we're you're going to read a homework problem that might say the words air standard in the assignment or the words cold air standard. And these are two different directions that you take when you're analyzing an internal combustion or external combustion engine. So what I want to cover is you're going to see those two words and say, how are they similar? How are they different? Why use them? And when to use one or the other? And also, what are some key solution approaches for both types of analyses? I've made a couple of screenshots right out of Chapter 9, so you'll see what I'm talking about. In problem 9.9 out of the textbook, it says an air standard Otto cycle, blah, 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 blah. So you see it says air standard. Well, then we go to problem 9.10, and here it says, consider a cold air standard Otto cycle. And it goes blah, 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 blah. All right, wow. Well, it's very subtle wording, but these are different, but they're also similar. And so that's what I want to talk about. In your homework assignments or getting direction from your instructor, okay, you're going to see two categories, the words air standard or cold air standard. And what that has to do with is modeling the substance, air. Well, for both of these situations, you're going to model air as an ideal gas. Ideal gas equation of state holds, calculating R, that holds, okay, all that. But the next decision in your decision tree thinking is, how do I model specific heat? And here's the big thing. When you see the words air standard in a problem, you're going to be modeling the specific heat as variable, kind of like a formula. But you don't want to have to do the integral all the time. So when you're looking for delta U or delta H, or analyzing an isentropic process, you're going to be using table A22 for air with variable specific heat. That's the bottom line. So over here, if you see the word cold air standard, you've still got air, you still got ideal gas, but your model for specific heat is constant specific heat. So if you're using the cold air standard analysis, if it says that in the problem, you're going to go to table A20 and you're going to select a value for specific heat. Or you'll be given it in the problem statement and you're going to use that as a constant. So that's the point I want to make, is when you're reading a problem, whether it's a homework problem or a quiz or a test, very carefully read these words. air standard or cold air standard. That's going to really dramatically change the way you do the computations of problem solving. Okay, so why use air standard or why use cold air standard? So we use these models to analyze the performance of both internal and external combustion engines commonly used throughout the world. We're going to use one or the other of these to analyze engines associated with these screenshots, these images. When would you use? So, of course, in this class, your instructor is going to guide you on using cold air standard or air standard. So it is my hope that you have a discussion about that selection in your classroom. But typically, you may choose to use a cold air standard, for example, on these internal combustion engines when the beginning state, in other words, the air intake model, is at atmospheric conditions, like sea level conditions, so that the state one pressure and temperature would be around 1 atmosphere and around 25 degrees C. That's a common time that we would use the cold air standard. CP or CV is a constant. Now let's look at this situation where you have an aircraft using two gas turbine engines to propel itself through the air at a very high altitude. So do you see that the inlet conditions to this gas turbine engine is going to be much less than 1 atmosphere because of the high altitude, and also very cold, much, much less than 25 degrees C. So that would be an example of when we would correctly use an air standard model, variable specific heat, to analyze the performance of our engine model. So not ambient atmospheric inlet conditions. So that's just an idea, but the key here is to get guidance from your instructor on what he or she wishes for you to do. How are these similar? Air standard and cold air standard, how are they similar? Okay. Well, they're both similar in that you're both analyzing a cycle. All right, so I've just drawn the schematic diagrams. And as a reminder, looking ahead in Chapter 9, remember, if you've got an internal combustion engine, you're going to be analyzing one single thermodynamic cycle, something that's going on in here, some number of processes, but your units for QH and W net and QL will be kilojoules or BTUs. Okay. If you're analyzing a system operating at a steady rate, you've got Q dot, W dot. Okay. And that's going to be an example of when you're analyzing the Brayton cycle or the gas turbine engine that's operating steadily. So both of these analyses, cold air standard and air standard, apply to these. Okay. So here's the recap. For an air standard cycle, your model is air, it's an ideal gas, and you're using variable specific heat. Use table A22. If you're assigned to use the cold air standard, you've still got air, it's an ideal gas, but your model for specific heat is constant. In other words, C sub P or C sub V is just some number, a number that you pick out of table A20. Okay. But it turns out that the process by process analyses are the same. The fundamentals are the same. The difference is in the way you evaluate the properties, delta U, delta H, and the way you analyze an isentropic reversible adiabatic process. So that's a quick overview of the difference between cold air standard and air standard. Students, including myself, have found it to be confusing. Which do I use? What do I use when? And I want to suggest that you have good, solid, respectful conversations with your instructor in the classroom meeting to get some clarity on the difference between those two and what your instructor wants you to do in homework assignments, quizzes, and tests.